today we actually have an amazing speaker, Ray. He's actually one of our mentors here for the program as well. And he's going to be talking about advanced Git. And I would love you to just kind of dive right in and give a little background on yourself, and then also to a little bit about what you'll be covering today.
Yeah, sounds good. My background is I've done a lot of stuff. I'm originally like in college. I originally trained to be a mathematician. I sort of escaped the math PhD career track, which it has good and bad points. It would have been nice, but academia is not really a pleasant place to work in a lot of ways. So I've worked in software for a while instead, kind of in a lot of places, out in San Francisco, here in New York. And yeah, I've happened to have developed sort of an interest in the theory of version control systems. And that includes Git, which is pretty common. It's actually a very good system for version control in a lot of ways. I don't say that lightly. There's been a lot of attempts at version control, and certainly Git is not perfect, but there's a lot of good things to recommend it. And what I'm going to be doing is I'm going to be making a Git repository and making some commits to it, but I'm going to be doing that in kind of a detailed and roundabout way, and digressing onto a lot of topics in the process. All right, and I am glancing off to the left because I have on my other computer my talk outline, including all of the commands that I want to type. So yeah, I'll go ahead and get started. So this is a talk about Git, and to do a talk about Git, you really need a Git repository. I have tons of them on my hard drive for various things, but when it comes to this, I'm going to make one. And so the command to make a Git repository is git init. Yeah, there we go. It's that's kind of boring. I do want to highlight, I have this extension in my shell that when I'm in a Git repository, it shows the current branch and so on. That's a handy thing to have. I'm going to be leaning on a bit at the beginning of this talk, and you'll see why. So initialized empty Git repository in et cetera, .git. Yeah, so you see I have that .git directory. Now we usually think of the whole folder, like in this case, the example folder, we usually think of that as the Git repository. But really it's the .git directory that's the Git repository, and the other stuff is just, it's kind of like a front-end user interface on top of the back-end database that is the Git repository. Let me just show you. There's a lot of stuff in that .git directory. The various components that you get when you do an empty Git repository, like that's what it is. So I'm going to go ahead and delete it because Git init is kind of boring. I'll direct your attention to my shell prompt again, where you can see I'm no longer in a Git repository. And let's try to do it manually instead. There we go. I made a .git directory, but my shell prompt, which is kind of the arbiter of whether I'm actually in a Git repository or not, it's not buying it. We're not actually in a Git repository, just because I made a .git directory. There's other stuff that's required. Let me direct your attention here. Now, a lot of this stuff isn't strictly required. You get it when you do Git init, but it's not strictly required. But a Git repository, basically, you can think of it as like a database. It's a pretty unique kind of database, and we'll see how as we go through this talk. But it stores two types of things. It stores objects and it stores refs. So they live in these directories. So I've made objects and refs directories where my objects and refs are going to live. But you see my shell prompt, it's still not enough. There's one thing missing. And the thing that's missing is the head. Now, what is a head? That's not a directory, so I can't just make a directory. It's actually a file. I'm going to put this sort of magical incantation, although it might look familiar to a lot of you. And that's enough. Now we're actually in a Git repository. The shell prompt has given it its blessing. Can run git status. So that's like the bare minimum that you need before to have a Git repository. Sorry, I'm scrolling through my notes again. Okay, so 2 directories and a sort of magic text file with a magic incantation, which is not magic at all. I'll reveal everything soon enough. Okay, now you saw that I need to use ls-a. It's a .git directory. The dot is, if you're not a Unix user, the dot in front means that it's a hidden file. Doesn't show up in normal directory listings. Now, I said before that the .git directory is the real Git repository, and all the source files and stuff that we normally think of are like a user interface, a front end on top of it. So I'm going to make another directory. I'm going to pass this --bear option to get in it. Okay, by the way, you can ignore when it says fatal. There's not actually a fatal error going on. Okay, initialized empty Git repository. What did that option do? Well, let's look. As you can see, it actually just made the Git repository. It didn't make a working tree at all. It's not in a Git directory. It's all just right there in the directory. Now, that might seem kind of useless, and it might seem like it's not actually that good, because normally you make a Git repository because you intend to commit things to it, right? So how can you commit things to this? It doesn't have a work tree. Well, there's another command that you can use to put things into a Git repository. You might have heard of it. It's called git push. So let me demonstrate that. I'll just clone my repository. Yes, I do appear to have cloned an empty repository. It's done. I suspect a lot of you have cloned things from URLs before. You may not have cloned things from a directory, but you certainly can. A directory somewhere else on your hard drive is a perfectly valid remote for a Git repository. The only thing that it has to be a remote is to be another Git repository. Okay, now we look at that. It's not bare. Bareness, like bareness is just a property of how the repository lives on your disk. It doesn't have any, it's not like a part of the repository that's a bare repository. It's just how you check it out, basically. So I didn't do clone --bare. I just did git clone, so it made a normal repository, and it does have a working tree. So that's good. Let me make a readme file. Okay, I made my initial commit to this repository. Now let's pause for a moment. Like we have a commit, that's good, but let's pause for a moment and look at the .git directory again. Okay, now you see there's actually quite a bit more stuff in it. Let's look at head again. Now head is it's like a part of the Git repository state. The head is, it's where you are now. If you check out a branch, you're on that branch, that means that the head is that branch. Now you can see what our head actually is. It's a little text file. It says ref, and then it says ref's heads master. Okay, so what's ref's heads master? Well, let me direct your attention to the tree I just did. It's literally something inside the .git repository. It's a file called ref's heads master. Or rather, the directories are refs and heads and it's master. But what's inside it? Well, what's inside it is a nice SHA-1 hash. Now these, you should get used to them. They're definitely all over the place in Git. And that's because of the other type of thing that you store in Git besides refs. objects. Now, you might have noted that it's called master, and I'm on the master branch. And what the master branch is literally this text file. It's 40 characters long. I guess I think it ends in a new line, so it's maybe 41 bytes. And that is the master branch. It's just a little text file with a hash in it. The hash is the hash of a commit. But what is a commit though? You can see up here this mysterious objects directory, which has suddenly spawned three new items since I did that commit. Okay, we might as well look at them. Now we have, you can see they're kind of stored into directories. Like the first 2 characters are a directory, and then the remaining 38 characters are a file name. That's just kind of so you don't have a single directory with way too many files in it. Because in a real Git repository with actual code in it and so on, you develop quite a lot of objects. So it's just a little niceness for the file system. So yeah. Let's go ahead and cat it. I'm going to pipe it into E. If you don't know what E is, that's okay. It's literally something that I wrote myself for this sort of situation, because it's actually, well, look, it's a binary mess. And the E utility, which I'm going to be using a few times here, is it just takes unprintable characters and it turns them into these red escape sequences to easily identify them. As you may know, if you just like cat them into your terminal, you can mess up your terminal, and then it's annoying. You have to close it and open a new terminal. I really don't want to do that. And I do want to see the characters, so that's why I used E there. Okay, I do have good news though. It looks like it's a binary mess that's going to be painful to actually work with, but it's not. It's just zipped with zlib. So I used a pigz-d. It's just a little compression utility to decompress it. Basically, all of your Git objects are going to be stored in this compressed format. And you see something with nice readable text in it. And you do see one, I did use E again because you do see 1 0 byte there that wouldn't be printable. And I want to highlight that it exists. So let's look at this. This little like sort of text file this is the commit that I just made. So let's look at it. Okay, it starts with the word commit. That's nice. Then 185. 185. This and then has a 0 byte after it. So everything before the 0 byte is like the header of a Git object. They all start with the same header. A word, which tells you what type of object it is. It could be commit, could be some other things that we'll see shortly. The size in bytes of the object, and then a 0 byte to indicate the end of the header, and then everything after is the object itself. And by the way, this size it's the size of everything after the 0 byte. It doesn't include the header size. So everything starting from this T to the new line after this T is 185 bytes. Okay, so let's look at what it actually says. You see this tree and then this mysterious, completely different SHA-1 hash. And you know, it might look familiar if you were watching the directory listing earlier because it's up there, and we'll look at it in a second. Got 2 more lines. You have author and committer. They're both me, my email address, timestamp. They're both the same timestamp. Why is it in there twice? Okay, so the reason it's in there twice, author is the original creator of the commit. Like I just created this, whereas committer is the last person to edit it, and the timestamps are the same. The time the commit was created and the time it was last modified. And then you see my commit message under there. And that's all a commit is. So you might be wondering, you know, where are the files? And it's likely that you guessed where the files are because I skipped over this tree 70, etc. I'm going to, actually I have a little script that's the exact same pipeline that I've been using, you know, the pigz and E and so on. So let me .git objects, and what's the hash? 70, 4a, etc. Okay, cool. What do we have here? we have the same header that we saw for a commit. Starts with tree, 34, that's the size of everything after it. Then we see some kind of weird stuff after it. So a tree object is a slightly, like it's the second, I guess the second most complex format that you see inside a Git repository. The most complex is the index, which I will not be describing the format of, but I will be talking about it.
Raymond, we did have a question in the
Sure.
chat. Is when I amend someone else's commit, do I become a new committer?
When you amend someone else's commit, the author stays the same. They're still the author. The committer will be you, yeah. And you may have seen, like, sometimes two people's pictures are on a GitHub commit. That's because the author and the committer are different. But the original author still has, like, the author.
Great, thank you.
Yep. Okay. So we have some weird stuff after the header because it's kind of a mixed format here. You see this 10644. You see readme, that's the file name, of course. Then there's a bunch of binary gibberish. What could this binary possibly be? Oops, sorry, I hit the wrong button. Do I hide this again? There we go. I hope I didn't like cancel my screen share or anything.
Nope, it still looks good.
Okay, awesome. Okay, so yeah, what is this this binary stuff after readme and then a 0 byte? That's actually it's a SHA-1 hash, which is kind of what you might have expected. But why is it in binary when all the SHA-1 hashes we've seen so far are just in text? The reason for that is that file names can have all sorts of weird characters in them. And basically the only thing that it can't have is a 0 byte. So the file name, you have first this mode number, which in this case is 10644. The 100 is it's basically saying this is a file. 644 is the file permissions. Then you have a space, and then everything after that until a 0 byte is the file name. It could have all sorts of weird bytes in it. And then after that, the format specifies the next 20 bytes, which is how big a SHA-1 hash is in binary. The next 20 bytes are the hash in binary, and then it immediately goes to the next tree entry. In this case, I only have one, so there's no next entry. It just ends.
I'm not sure. Sorry if you answered the question already, but someone asked, did you happen to mention why the first two characters in the hash are a directory?
Yes. So it's you mean like why the objects are stored in like first two characters and then remaining characters? Yeah, I did mention that. It's just basically it's easier on the file system if you don't have many thousands of files in one directory. It just kind of segments them a bit so that your actual file system, like you don't have performance degradation from trying to list and work with gigantic directories, which can sometimes happen. All right, so yeah. Now we could sit here and parse this this binary stuff and get a better view. There's not actually a need to, because Git has a built-in plumbing command that will do exactly what I want for me. It's printed the tree object that we were looking at in kind of a nice format that looks more like a directory listing. It has the SHA-1 hash in text as we might want. You notice, I just want to draw your attention to, I didn't put in the whole 40 characters. So basically in Git, you can always use shortened SHA-1 hashes, like 6 characters is common. Basically, as long as if there were 2 hashes that both happen to start with these exact 7 characters, you would not be able to. You'd have to add another character. But as long as it's an unambiguous prefix, you can use shortened hashes for any Git command, really. I think it actually stops you Yeah, it stops you if there's too few, even though there isn't actually anything else that stops with 7. There's like a minimum of, I don't remember how many, but basically you can always use a short prefix. Okay, so now we have a nice view of this. You can see the 10644 again. You see a blob. You see a third SHA-1 hash, the third one that we saw above, and you see the file name readme. How do I keep doing that? Sorry. Yeah, I keep hitting escape kind of on instinct. So you see this third SHA-1 hash, and we might as well look at what that object actually is. Sorry. I just not tab completing it right. There we go. Okay, this is basically the simplest of all. It's just the Git header ending in the 0 byte, and then the contents of the file. So you see 5 characters, a new line at the end, so it's 6, and it's a blob. That's all there is to it. So that's what we actually have in the database. We have refs, which basically, more or less, they just have a SHA-1 hash of a commit. And you have these other 3 types of objects. You have commits, you have trees, and you have blobs. Trees are they're like the directories of Git. A tree can have blobs that it points to, but it can also have other trees that it points to. That's how it works if you have subdirectories. And a blob is just a blob. It is what it is. Those are the files of Git. And aside from the header, they're just the file. And let me do the SHA-1 sum of my readme. You can see that it is not the same as the SHA-1 sum of this object. Why is that? Well, it's because the SHA-1 sum includes the Git header, this blob6 0 byte. So let me just blob6 0 byte, concatenate it with readme, type that into SHA-1 sum. That's what we have the SHA-1 sum of. You can see these SHA-1 sums are exactly the same. And then going up the levels, it's the same with the tree objects, and it's the same with the commit objects. And what a consequence of this is, we'll see one consequence of it in a moment. Another consequence of it is if anything changes, then the hash will change, because that's how hash functions work, which means that the whole object will change. So like that's why when you amend someone else's commit or amend your own commit, that's why it becomes different, because the hash includes this line, committer, et cetera, et cetera, et cetera.
One question that has popped up is, can you explain a little bit more about what a blob is? Some may not have that context.
Yeah, I mean, the blob it's just this. It's the file. And remember the contents of our file are hello. So it's literally just the file that I committed. But it has this header on front to tell Git that it's a blob object. And then it's hashed and stored in the database by its hash. And that's the same way that any file is stored. And you may know that Git doesn't allow you to commit empty directories. I guess, I guess in theory you could have like a 0 length tree object, but it's not something that Git allows. It only allows tree objects that actually have children. Okay. Next. We're done with those repositories, and we can go back to our original example repository, which you may recall we just made it with the minimum possible. We haven't done anything yet. And okay. You may have noticed I have this visual aid over here. The actual image here is not relevant to anything, but it will become relevant in just a moment when I'm done setting it up. Let's see. I couldn't find any utility that did what I want to do here. So for that reason, I coded one up. It's like a really quick hack job. Has a lot of deficiencies, but it does more or less what I want for the next portion of this talk. So I'm going to go ahead and use it. As you can see, this is just an image viewer. It'll update every time I run this command. And right now we have an empty image. And that empty image is accurately displaying the state of our repository right now. There's no objects in it. There's not even any refs in it. There's just a head that points to a master branch that doesn't exist yet. So let me go ahead. This one will be a capitalized hello. Okay. Now I'm going to git add. All right, what have I done there? Well, so git add does two things. It takes the file that you added and makes it into a blob object and puts the blob object in the database. See, it's in the database now. Sorry. And it's shown up on my little visual aid here. There's nothing else in the repository, so it's kind of a lonely blob right now. The other thing, and you can see it here in the tree, is the index, which I'm not going to talk about that much, but is pretty important to at least know what it is. Okay, the index it's actually kind of a complicated binary format, unlike the easy formats for objects that we've seen before. So I'm not going to explain the format. I certainly don't remember how it works. I would have to look it up again myself. You do see the file name readme in there. Basically, the index stores everything that's about to be committed. So in this case, it stores various pieces of information, but one thing it stores is the fact that this blob in the objects folder, this blob whose hash starts with E96504, is a file at the path readme, so that when I actually do the commit and the tree object is built, it knows how to build it from what's in the index. And unfortunately, it's kind of a complicated binary format. So I'm going to go ahead and commit it. Okay, let me update this. All right. So we went over this before in the other example repository, but let's go over it again. So we have this blob object that was already in there after I did git add. Now there's a tree object, which I've represented by these trapezoids. The tree object contains a reference to the blob object. And then we have finally on top a commit object containing a reference to the tree object. It's very nice and it's very simple so far. But you can't have a project with just a readme, especially not a project with just a readme that just says hello. Let's go ahead and make a git ignore. Let's do that. Yeah, okay, I can't hit escape here without popping that up. Just move this down slightly so it doesn't get in my way. Right, good. Okay. Add .git ignore. Now let me update this again. Okay. So you see we have a new blob in there. It's not connected to anything. But it's just wanted to point out again that git add does make blobs. Okay. So I'll commit it. and update. Okay, now we have a somewhat more interesting graph here. Okay. Let me draw your attention to this red arrow here. So now that we have two commits, like you'll notice that they both look similar. We have this commit points to a tree, this commit points to a tree, as we expect. Every commit points to a tree. That's how we know what files are in that commit. We have this red arrow, a commit pointing to a commit. Let me drag out git cat again. Okay, we have a new type of line we didn't see before. So we have tree 4e76, you can see that here. Now we have parent 3dd41, et cetera, et cetera, et cetera. That, and I highlighted these relationships with red arrows because they're a bit more important than the other types of relationships, at least from the perspective of what I'm trying to talk about today. So a parent, we didn't see it before because we only had one commit every time we looked at a commit before. But a git commit can have 0 or more parents. The parent of a commit is the commit that came right before it, basically. And I said there can be 0 or more. Most commits have one parent, which is the commit that came right before it in the history. Some commits have 2 or more. Those are known as merge commits. They serve to sort of unify strands of history. And we'll definitely merge some stuff shortly. Okay, but now let's look at the rest of this graph. So they each have an individual tree object. That makes sense. We did change something about the tree. So it only stands to reason that there would be different tree objects. Let's look at the blobs they point to. Here's a new blob, our .gitignore file. But you see both trees point to this same original blob, our readme file. So this is a very neat thing about Git. You get data deduplication automatically because of how it stores objects. If an object is the same as another object, then when you make it into a blob, or rather, what I mean to say is if a file is the same as another file, when you make it into a blob, then it's going to be exactly one blob. The contents are the same, the size is the same, and the word blob that goes at the front is also the same. Let me demonstrate that. We're going to copy readme to readme 2. It's kind of an improvisation, actually. Okay, cool. This got bigger and a bit more complicated. So what do we see here? 2 arrows pointing to the same blob. This is our new commit that I just made. It's hashed. It starts with 3ef, etc. The tree that it points to is this one. What does that tree have in it? 2 files that are both the same, readme and readme 2. Now their file names are not the same, but if you remember, the file names are stored in the tree object, not the blob. The blob is just the contents of the file. And then, of course, we have the original readme. Or rather, no, this is the readme, and we have the .gitignore, which is still in there. Like our initial commit only has one readme. Then we have a .gitignore. Okay, that's kind of neat. That was also kind of improvised. So I hope it doesn't screw me up later. Let me do another weird thing. Normally, if you try to do a commit with nothing, Git doesn't allow you. That's why I put that extra option, allow empty, to override that. Update this. Okay. Now you see, this is our previous commit that we were on. That was 3ef, etc. We have a new commit, but we didn't change anything. It's a new commit, to be sure, but they both point to the exact same tree object. So this is if you think about it, this is a very natural thing for a version control system to do. With a version control system, a lot of times you have a big project source tree with tons and tons of files. But when you make a commit, you're usually only changing a few of these files at most. It makes sense to just keep pointing to the exact same objects for every other file that you didn't change. Okay, what's next? We're going to make this more complicated. I'm going to start a feature branch. Okay. And remember, branches are just text files. Master is still where we left it. We didn't change anything for master. But suppose I make my branch and I start it instead. From the initial commit. Like you can point a branch anywhere. Like the branch isn't the reason they're called lightweight branches is because they're literally just 41 byte text files, and you can just move them around as much as you want. It contrasts with earlier version control systems where when you did a branch, you would literally copy the entire source tree into sort of another repository sometimes. Like that's how it worked with Subversion. I think CVS was a bit better about it. But anyway, you can see we're on the first commit because there's no .getignore and no improvised readme2 file. Okay, let me just write a quick program. Okay, cool. Great, I have a program that prints hello. Okay. Let me refresh this once again. Okay, it's gotten bigger. Okay, it's gotten bigger. I added 2 new files to it. I mean, I ran the program, it worked, so I'm going to commit this. Refresh this again. You can see our graph keeps getting bigger and bigger and starting to approach the point where it'll get too big to use and I'll switch to another program. Okay, so remember, here's our initial commit. All the other stuff we did is in this line. And here's our new commit. Now you'll notice literally every tree object here has some kind of reference to our README, at least one reference, some have 2. You can see I added 2 new files, that makes 2 new blobs. Let's see, that's about it. Our graph is getting a bit more interesting, and I'll make it, I guess, 1 step more interesting while I still have it. I'll do a merge. Okay, that's good. Okay, this is like the maximum complexity that this little graph visualizer can handle. So I just added a new commit. When you do a new tree, there's a whole mess of stuff. Basically, it points to every blob because I merged everything and now has every file. You see, just like I said, commits can have 0 or more parents, and for the first time we see one that has 2. What's the hash of it? 36C1. There we go, 2 parents. That's the only thing that makes it a merge. There's nothing special about it as a commit. It's exactly the same as every other one. It just has more than 1 parent. Okay. And it did update master. Now I'm going to bid farewell to this hacked together thing and start up a different program that's less hacked together. Let's see, open the Git repository. Okay, so why didn't I use this to start with? Because it only shows commits, and I wanted to show trees and blobs for a while. But I think I've said all that I have to say about trees and blobs. So we have this. This is a bit nicer. You can see this is the graph of just the commits. Here, 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 here. Here's our feature branch off here, and they get merged together here. And I'm also going to be using at some point git k. This is something that comes with Git, although you may need to install. You may need to install like a git x11 package, depending on your system. This is just the repository viewer. You can see the graph here, and you can see information about the commit here. So I'm going to be using both of those for different things. The good thing about this program is it updates in real time, so it's just going to be sitting there throughout the rest of this talk. Should be good. Okay. I can delete the branch feature now. You see I'm using this lowercase d. If you use a lowercase d, Git will refuse to delete something that you haven't merged. In this case, it's happy to delete it, and you see it disappeared here. Now the commit's still there, of course. The commits are different from the branch. The branch is just like the branch is literally just the line pointing to the commit. You can think of it that way. And I don't need it anymore because I merged it into master. So I could just go ahead and delete that. Okay, now I have all this complicated history here. I don't really care about it. I'm going to go ahead and blow it away. And the reason I'm blowing it away is it's not for simplicity, although it helps a bit, because I want to demonstrate the interactive rebase feature. You see, we've opened up a nice text editor with a little script in it, kind of. This is really like a miniature scripting language that tells Git what to do. Now this is kind of a simple concept, but also a complicated concept. And actually, I do want to.
While you're doing that too, we had a question.
Sure.
In terms of Git objects, what would a fast forward do?
A fast forward only touches refs. I will mention fast forwards later when I start doing some more merges. But like imagine that master was pointing here, and a valid fast forward would be to just move master there, for example. And it doesn't actually create a commit, but I'll get into that in more detail.
Great.
So I do want to draw your attention to the red arrows. There was a secret reason that I highlighted them red besides making them easy to see. And it's kind of important for understanding what this interactive rebase is actually doing. So as we were looking through the repository and looking through all the objects in it, basically like a commit object points to a tree object, right? So what is a commit really? A commit is a snapshot of a source tree at some point in time. It's got some extra data like who wrote this commit and so on, and a message. Basically, it's a snapshot of the source tree at some point in time, right? But the tricky part is that sometimes it isn't. The tricky part is that 3061A3 sometimes means this box here when in the contents of the tree object 8CD209. But sometimes commit 3061 means the red arrow. And actually this one has 2 red arrows, so there's different things that can mean, but let's look at 8C OOC. Like sometimes it means, this, sometimes it means this red arrow. Remember, this was an empty commit, so the arrow actually does nothing. What I mean by that is visible if you look at git k. And you'll notice this has changed, but don't worry about it. I'm going to explain that. Okay. So a good thing about git k is that it shows you the commits down here, right? So when I added .gitignore, what did it do? It added basically it created a new file. It added 2 lines to it. But this commit is also a snapshot. It's this tree at this point in time, which has 2 files, .gitignore and readme. And the tricky thing is that in some contexts, when you give a hash or a branch name or something to Git, in some contexts it means the commit as a patch. In some contexts it means it as a snapshot. So I'll tell you right now, whenever you're doing any sort of sorry, I messed something up and I'm resetting it.
As you're kind of working on that too,
Yeah.
Another question was, does Git internally care about diffs at all, or is that only for the programmer?
Yeah, so the answer is, as far as the database perspective, everything is just trees and blobs. As far as the actual things that the program does in real time, it absolutely does care about diffs, as you will soon find out because I'm covering rebases. So the thing about rebases is exactly that. It's exactly what you say. Whenever you're doing a rebase or a rebase-like operation, all of your commits are no longer, you can no longer think of them as snapshots. You have to think of them as the diff now. And so when you do this, it's saying, pick 3DD, pick 9CC, etc. So that's saying take this commit and apply it, like apply the patch, apply the diff, make the change, and so on. It's not saying take the snapshot at this time. It's saying take this commit viewed as a patch rather than as a snapshot and apply it. So like if I reordered these, it would actually make a difference, for example. It would make a difference between some of them because some of them don't mean anything. But like if I reordered add.gitignore and initial commit, then you'd have a repository where the first commit inserts a .gitignore and the second one inserts a readme. And like if I were changing files rather than just creating them, then you would see sometimes you wouldn't even be able to reorder it because it would cause a conflict because maybe something depends on something else. Like maybe you add a function and then you change the function. You wouldn't be able to change the function before add the function. That would cause a conflict that you wouldn't actually be able to resolve because it wouldn't make sense. There would be no resolution that made sense besides going back and doing it in the correct order. Okay, so how do I commit? How do I pick a commit? I view it as a patch and I apply that patch. That's what this script is doing. And you'll notice I did have a merge, but this is just a list of commits. And if I actually, if I as I mistakenly did earlier, if I just go ahead and let it do this now, it'll actually remove the merge because it'll just take 5 commits and apply them. I don't want to do that, so I'm going to give it an empty file so it does nothing. I just want to, I'm not going to go into this deeply, but I just want to show you this is actually when I say it's a scripting language, I really do mean it's a scripting language. Like you have labels and go-tos here and so on, but it's a scripting language that builds up a git commit graph. So you can see the script that generated because I told it to preserve merges. What it does is first it makes that feature branch, like it makes the initial commit, then it makes this, then it goes and resets to the initial commit. It makes all of these commits again, and then it makes a merge. So if I ran this, things would be unchanged. But neither of those things are actually what I want to do. What I want to do instead what I want to do instead is meld everything into one initial commit. Now you can see the reference for the language here. There's a lot of commands we can use. The ones that are relevant here are squash and fix up. Okay, use commit but meld into previous commit. Now if you've ever used commit amend, what that does is it takes something and instead of committing it, it just adds that change to the existing top commit. Well, squash and fix up, and I'm using fix up here because I just want the message to say initial commit. I don't want it to say all of these lines. So what squash and fix up do, they just do the exact same thing, but with commits that already exist. So this is what I actually want to do. And when I do it, I'm going to have one initial commit, but it's going to have everything in it. There we go. And actually, sorry, but I'm going to remove readme too. I'm afraid it might get in my way. But you'll see it was a bit slow to update, but you'll see that this visual aid over here has indeed reduced itself to one commit. Okay, so now I have one initial commit and it adds all these files. Okay. Now I just want to point out, it looks like I just went and deleted the history. Actually, it's really hard to delete something in Git, especially once you've committed it. So let me introduce you to git reflog. So literally every time that you do something that changes a ref, and by the way, head doesn't live in the refs folder, but it's considered a ref. It's like a special one with more importance, but still a ref. So literally every time you change a ref, like here's the history of head, here's the history of master. Every time it gets saved in the ref log, and you can think of it as like sort of an undo history. So what I see a lot of times is people who like beginners at Git, but also people who are experienced with Git, but not very comfortable with it. What I see them do a lot of times is they do something, it doesn't turn out how they expected. They think they lost data. And the reality is it's very unlikely they actually have lost data. Except what a lot of people do then is go ahead and panic. They delete their repository. And now they have lost data because they deleted it. So what I strongly encourage people to do is if you do end up in a situation like that, don't panic, delete your repository. You may have to look at the ref log. You may have to check out these things. You see this syntax like master at and then one in curly braces. That basically means master one step ago and master 2 steps ago and so on. So you can definitely get back to the state that you wanted it to be in. You'll find it in the ref log, basically almost by definition. Now it's true that old stuff does get garbage collected, but I looked it up recently because I was on a call with someone talking about this stuff. I looked it up recently. It gets garbage collected by default after 90 days. So I think if it's basically these data loss emergencies that people sometimes run into where the data isn't actually lost are usually not 90 days long. So I basically don't panic. Like I see people who are very experienced with Git panic and delete sometimes. I would just like to encourage you not to do that. And that's my PSA here. So let me. I just want to put it back onto my visual aid again. It might take a second. There we go. Now it looks a bit weird because head is over here, but you do actually see the old history. Like it's all still there. And then you have, you know, the new cool master that I just created is here. Let me go ahead and delete that. I just wanted to show. Okay, that's good. Now let me get to some programming quickly. So there's a few things that I want to do, right? I want to go ahead and make a release of my really cool example program that prints hello as standard output. So there's a few things that I need. First thing that I need, and let me just this here. Okay, I have 3 tasks, and I'm going to make 3 branches for them. I want to add make clean to the make file because you know, I don't want to have to manually remove the object file after I compile. I want that to be there. I want to be able to install my program. It's very important. And finally, I want a version option. I want to print the version of the program. Okay, so I made 3 branches for them. Let's see. Cool. Now, here is where there's like kind of 2 different roles that you play when you're interacting with the Git repository. One role you play is the coder who writes code and commits it. The other role we play is the maintainer. Now, even when I'm doing a solo project, I like to split concerns between being a coder and being a maintainer. So basically my rule for that is the master branch it belongs to the maintainer, and every other branch belongs to the coder. So that's why I made all these branches. Okay, I'm just going to very quickly code up what I actually want. Okay. What's the syntax for this? I think it's Okay, there we go. I've made a few changes there. I added that one a bit prematurely. So I could commit all of this here, right? But this change actually has a few logical parts to it, and that's kind of why we have the git add command to begin with. And actually, I did do the right thing, because I want to do this in 2 commits. Okay, but wait. When you think about it, my changes to the make file only make sense if they're in the same commit. So actually, I just amend it in. There we go. Okay, I've just completed all of the features that I need to complete to make a 0.1 release. So let me go ahead and merge them. Now, maintainers do different things. Some maintainers would like to take all of these branches and just rebase them all into one line. That would take a few steps, but basically use the git rebase command. Let me show you. So like master is here, right? So I would say I wanted to do make clean first. I would fast forward master to here. Let me just actually do it. First, I'm going to undo this in seconds. Let me save my position by making branches. This is something handy you can do. You can always make a branch before you do something. And then the new branch that you made will just stay where it is. So if you ever want to go back to that position, you can just use the branch that you made. I'll do the same thing. For all of those. Okay, cool. Now I don't actually do this, so I'm going to be glancing over at the commands I wrote for myself. Right. Okay, what does this command do? It actually, this is just a shorthand. If I put 2 things here, it just means it checks out make clean first, then it does git rebase master. And what that does is it takes everything on make clean that's not already on master, and it replays it on top of master. But the thing is, master is only 1 commit now, so that command is actually not going to do anything except check out make clean, which is fine. But now we get to the fast forward part. And you see I'm passing a fast forward only. If you don't pass either no FF or FF only, then Git will sort of try to decide on its own whether to fast forward or whether to make a merge commit. It may not decide what you want. I just kind of out of habit always pass these options. So FF only, which would make clean. Okay, fast forward only, make clean. And you see a fast forward happen because now master was here, now master is here. And actually, since I have master checked out, this head label will follow master. So that's what a fast forward is. It's when you merge something that's all just direct descendants of where you are now, you have the option to do a fast forward merge where instead of making a merge commit, you just push master forward in time until it's there. Okay. Anyway, now this branch is fully merged. Delete it. Okay, I'm just, there we go. Now you see what happened? Versions, okay, so this arrow, this is master, like this green line here points to where master is. And then now versions is suddenly, it originally started out here, but now it's just in a straight line on top of master, which means that the fast forward will succeed. the wrong command. That's literally why you have the lowercase d option. Okay. And there we go, this updates. And you see now master has fast forwarded again. Now master contains even more commits, which is good. Go ahead and delete that branch. Now finally, and if you've been following closely, you know that this is going to fail and result in a merge conflict. Let's go ahead and do that. Okay, so what's happened here? It looks like a bunch of stuff, but actually, this is sort of somewhat important information. Okay, it could not apply add install targets to make file. I have to resolve all conflicts manually. What does this mean? It just means that the patch expected a context that wasn't there. It expected a different context, and you can see what that is. Now, by default, the conflict style, it just has the left chicken tracks, the equals, the right chicken tracks. So actually, so I have this config setting set to diff3, which is important because it shows me actually 3 things, and just one of them happens to be empty right now, but it shows me what it was, way back in the common ancestor. So in this case, way back here, what it is on the left side, which is the master branch or whatever branch I'm trying to merge into, and what it is on the right side, or whatever branch I'm trying to merge from. And so you can see it's pretty clear what the correct resolution here is. Those are both phony. Don't need 2 phony lines, and I need all the targets. Since this was rebase, I continue it by doing rebase continue. There we go. All right, and now everything is there. You can see the original branches I'm going to go back to in a second. But okay, yep, now it's all here. All right. I have to actually do the merge. Okay, now they're all there. And everything works. It all worked nicely. And the most important thing is that it all ended up in a straight line. The reason I did all of those rebase operations was exactly to end up with this result. Some maintainers like to do this. I did it first because it's not actually what I do. What I do is the other style with a lot of explicit merge commits. But there are benefits and drawbacks to both styles. The merge commits contain useful information, which I'll talk about shortly. But some people just like to have one straight line and think that that's a cleaner and easier way to read. They're both right and they're both wrong, basically. And what it comes down to is just the personal preference of whoever maintains the project. So we go ahead and I'm just going to go ahead and undo everything that I just did. This branch-m option is it's for renaming branches. I think you can't rename a branch that you have checked out, but you can rename other branches. Okay, let's do it again, this time with merges. I think the command here is somewhat simpler. You make a new commit, so you have to edit the message for it. There we go. You can see it over here. Kind of this faint line is the branch we just merged into one commit, and there at the head. Okay, that's good. Merge the next branch. There we go. See, again, you have a branch. It starts there, has some commits on it, gets merged. That's fine. Now let's do the one that will trigger a conflict. Okay, we're in a conflict, but please take note of what it says here. Sorry, wrong line. Please take note of what it says here. Resolve make file using previous resolution. Okay, so this is not enabled by default. But you can enable it with git config. I have it enabled. This is something called git re, which is kind of a cutesy short name for reuse recorded resolution. Basically, what it does is every time that you come across a merge conflict and manually resolve it, it stores the resolution of that conflict. Then if you ever come across the same conflict again, instead of stopping and waiting for you to fix it and asking you to fix it, it takes the recorded resolution that it already did. It goes ahead and uses it. It does stop here so that you can make sure that it's actually correct. But I know it is correct. And to continue a merge, you actually do a commit. Okay, very nice. I want to go back to gitk for a second to show you something kind of neat. So like normally if you have a merge commit in gitk and you look at the patch, you don't see anything, which makes sense. The merge commit doesn't introduce anything new, right? It just combines stuff that was already there. But when you resolve a conflict, it actually does introduce something new. And what's kind of cool is that it's color coded. So you see this first parent is red, the second one is blue. And you actually see lines from the first parent, or lines from the first parent are in red, from the other are in blue. And then stuff that got introduced specifically in the merge conflict resolution, like this line, are bold black. So that's very handy, something that you can see with gitk. So like you might think that that's good, right? And that's the correct way to do it, right? But not quite. I'm going to undo everything again. It's kind of a theme here. Okay, now I'm back here. I just unmerged all my branches. There we go. You may have noticed earlier that I never actually said a merge commit has two parents. That's because it's quite true that it has two or more parents. It can actually have as many parents as you want. This is called an octopus merge. Octopus merges are quite fun. And basically you can just take as many branches as you want. Go ahead, merge every single one of them all at once. The only caveat is that if any of them cause a conflict, they have to be the last one on the command line. So you can see I put that make install one last. If conflicts arise earlier in the merging process, because it actually just does all of these at once and only makes one commit. So if conflicts arise earlier, then it'll just tell you, no, don't do an octopus like this. But you can have a conflict on the last one and it'll still work. So I do want to pause here to show something kind of neat. Let me just open a new terminal.
And while you're doing that too, we just have about 10 minutes, so just a 10-minute warning.
Sure. Okay. This is going to freeze my computer for a bit. So I'm going to sip some water while it freezes. All right. This impressive thing here is from the Linux kernel history from 2014. You can see it is it's still freezing my computer. It is a 66-way octopus merge. It was described by Linus Torvald as the Cthulhu merge. While he likes octopus merges, but this one is kind of a bit far even for him. Like as you can see, aside from freezing my computer, you know, Git K kind of ran out of colors. It does have a lot of colors to color with, but it ran out after like, I don't know, 15. And this thing just keeps going. It's like one of the really impressive things that Git is able to do. And I'm just going to go ahead and kill that now because it is killing my computer, which is a poor aging MacBook Pro. So that's the Cthulhu merge. Let's see. What's the next thing? I think I have time to do one more neat thing. So let me. Yeah, I'll do one more neat thing.
As you're doing that, we have let's see, how useful is octopus merges in practice, though?
Extremely useful. Like the thing is, basically there's not actually any meaning to whether a merge came here or came there or came first or came second. So I think that basically octopusing things in a batch is more meaningful and makes more sense. So like when you think about the master branch, there's two parts to it. Like if you look at the first parent log, where you take the merge commits and only follow the first parent, so you only see like the master branch itself, not stuff you merged into it. It's kind of like a list of, not a list of code changes, but a list of actions that the maintainer took. And then so like this actually says something. It says that at this point in time, I, the maintainer, took a bunch of branches and merged them. It's like an accurate description of what I did. And like this just comes down to personal preference of the maintainer, whether they think it makes more logical sense to do it this way, or just whether it makes more logical sense to just do individual merges for everything. Or like maybe it depends on the amount of detail that they put in the merge commit messages. Okay, so I'm going to show one more thing. I have here a nice docs repository that I made for my thing. You know, it's docs for my program, but they're in a separate Git repository. You know, and let's say that I decide, you know, it was a bad idea to put these in a separate Git repository. What's something that I can do? I can actually merge two completely unrelated Git repositories, and it's kind of a tricky operation. And that's why I wrote down the exact commands that I need to use for it. Okay, so here I am in the docs repository, and like basically it has this one docs.txt file, which sort of, it represents like a full set of documentation for a real program. Anyway, the first thing I'm going to do is I'm going to use sort of a heavy-duty power tool. It's called Git filter repo. It's like the well-oiled chainsaw to the rusty chainsaw of Git filter branch, which is a bit older, that you may have heard of. Filter repo. That should be the correct thing. There we go. What did I do there? I just rewrote the whole history of the repository, which was 2 commits, but like the whole history of the repository. We're pretending it's larger. So that everything was basically always inside a docs folder. I did that in preparation for merging it because it's going to be in a docs folder when I merge it. So back to this. You might recall from near the beginning of this talk, that you can just add a directory as a git remote. And I just added it as a remote. I fetched it, and now I have to pass this allow unrelated histories option in. So I'll merge the master branch of the completely different docs repository into my repository. Okay. Now you can see here, there's actually two initial commits. There's this initial commit, this initial commit. They go forward. They meet here at the head. Might be a bit clearer if I do it from git k, because I have the nice topological sort here. Yeah, so right now I merged this remote tracking branch docs/master, which was actually from a completely unrelated repository. Needless to say, when you're doing this with like real repositories and real history, it's a bit of a more delicate and involved operation that you want to take slowly and avoid screwing up. But in this case, since it's just a very simple sort of demo repository, it was pretty easy to just go ahead and merge it in. And now if you look at the files, you have docs, the docs folder, always right with the world. Actually, just do that since it's easier to see. Docs in the docs folder, always right in the world. I didn't delete any history. I did the filter repo thing rather than like putting a commit that moved them all into a folder, because one, that would break git blame, because now everything would blame to the commit where I moved it. And second, even putting that aside, like the rename tracking in git is kind of spotty. And so rather than doing that, and yes, the inverse operation is actually possible. I can take a subfolder and cut it out as its own repository. Okay, so I have this clone of the example repository. It has everything there. Let me use filter repo again. There we go. I just rewrote the whole history as though only the docs folder ever existed. And you can see, there we go, only these two commits are now there. So both of those directions are possible. See, I think I'm about at time, so I'll just take any final questions now. I'll sip some water. There was some other stuff, but I was really bad at estimating time.
You're fine. That was all extremely helpful. One kind of off-topic question was, when you did the octopus, is that the reason the GitHub mascot is an octopus? Do you know if that's correct?
I don't know, but I think that the answer is yes.
Oh, octocat is.
Yeah, the octocat. I think that the octopus part of it is a reference to octopus merges. I'm not 100% on that though, but it's what I believe to be the case.
Another question is, what did filter repo do in the first case?
So in the first case, it went through the whole history of the repository and replayed it, but it replayed it so that rather than just being docs.txt in the root of the repository, it was docs.txt inside a folder called docs. It basically like redid the whole history so that everything was already inside that folder.
Wonderful. Any last questions from the group? Could you show the command for that again, for that filter repo?
Yep, I could. So one of them, this is like the one for cutting it down to a subdirectory that's there, git filter repo, subdirectory filter. Then the previous one for moving things into a subdirectory across the whole history is git filter repo to subdirectory filter. And the reason I gave it the force option there is just because git filter repo, it complains if you do it on something that isn't a fresh checkout, or a fresh clone rather. Like it doesn't want you to take repositories with actual work in them and start applying this really heavy duty power tool to it.
We had a recommendation for a part 2 of this talk because it was super helpful.
Yeah, I mean, there is actually other stuff I had in my notes. I ended up with like 8,500 words of notes and stuff just because I had no idea whether I would go long or short. So there is more stuff that I could do in a part 2.
Yeah, you're getting a lot of yeses to that. I think a part 2 is make it a series is what we're hearing now. So
yeah, I'd be glad to do that. There's definitely more stuff that I have queued up. So
wonderful. All right, well, this just takes us to time. So unless there's any other questions, we will call today. We're getting some thank yous and all the Git talks is what people want. So thank you so much, Ray, for taking the time to do this, and hopefully we'll do it again.